In this video, we'll discuss SAIS algorithm. SAIS algorithm calculates suffix array by induced sorting. Here we'll discuss only half of this algorithm. We need to find the category of each suffix of the given string. Our given string S is dabrakadabrak, and we attach to it $sign. $sign is just a sentinel character that doesn't occur anywhere inside the S, and also it is the smallest alphabetically character out of all characters in S. We need to categorize first each suffix of S by a larger or smaller L or S type. To do this, we assign S type to $sign because it is the smallest suffix, so we put S, meaning small type, and then we go from right to left, and if current character is greater than the next character, then suffix would be L type. If current character is less than the next character, then the suffix will be S type. If characters are the same, current and previous, then you just copy the type of the next character into this current entry. R is greater than A, so it would be L type. B is less than R would be S type. A is less than B, so it would be S type. L, S, L, S, L, S, S, L. Now we need to choose out of all these suffixes, we need to choose LMS suffixes. LMS stands for leftmost S type. What does it mean, leftmost S type? It is, first of all, has to be S type, on the left of which the suffix is of L type. So this is S type, and on the left of it we have L type, so this suffix at position 13 will be LMS type. S on the left is L, LMS. S on the left is not L, so this is not LMS. S on the left is L, so this will be LMS type. LMS type, LMS type, and LMS type. These LMS type suffixes partition the entire string S into LMS substrings. LMS substring starts with LMS character and ends with LMS character, and no LMS characters are in between. So let's list all LMS substrings. Star means this character is LMS character, so we need to start with the LMS character and end with LMS character. This LMS substring starts at position 1, so starting position is 1, and the substring is A, B, R, A. Algorithm itself doesn't really list any LMSs, but just for us to understand what LMS substrings are, we're going to list them all together with their starting positions. Next starting position is 4, it goes from 4 to 6, so starting position is 4, and the substring is ACA. Next starting position is 6, substring is ADA. Next starting position is 8, and substring ABRA. And next position is 11, and substring is AC $sign. And the next one is $sign. $sign is the only substring, LMS substring of length 1. It starts at position 13 and it is a $sign. Now we have everything we need to fill in, start filling in suffix array. We need to go first put position of LMS substrings. You need to scan type array that we constructed here from right to left, and if the current position is LMS substring, put it at the end of the corresponding C bucket. First, let's find C buckets. There is only one character, $, and $, is smallest of all, so $, will go right in here. This would be C bucket for $. Next smallest alphabetical character is A. Count how many A's it has. 1, 2, 3, 4, 5. So we need to have 5 positions for A. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All suffixes starting with A will be in these positions. And this would be bucket, A bucket. Next alphabetical character B. 1, 2. So 2 B's we have. Next alphabetical is C. We have 2 C's. And D, 1, 2, 2 D's. And finally we have 1, 2 R's. This would be R bucket. All suffixes that start with A will be sorted alphabetically in consecutive rows, so their starting positions will occur in consecutive spots in the suffix array. And so is true with suffixes that start with B, C, D, and R. So we subdivided suffix array into the buckets, and now we're ready to put LMS starting positions into the end of corresponding buckets while we're scanning from right to left. LMS 13 goes to this bucket, 13 goes to this character bucket. This is LMS type. Look what character it is in the S string. This character is A, position is 11. Position 11 goes at the end of the 8th bucket. Next position is 8, character is A. 8 will go at the available end of the A bucket. The next available spot is this, so 8 goes right in here. Next one is 6, also A. 6 will go right in here, the end of the 8th bucket. 4 is A. And 1 is also A, will go right in here. We put all LMS starting positions into our suffix array, and now we need to do 2 scans. The first scan is left to right. In this scan, we looking at the valid content of suffix array, subtract 1 from it, and looking at the character in the given string S at that position if it is of L type. So if L type, put it in the front of the corresponding bucket. If it is L type, put it in the front of the corresponding bucket. How do you find bucket? Look at the character of the string, corresponding character. So let's do that. Assume that everything else that is not filled in suffix array right now is -1, which is invalid value. 13 minus 1 is 12. Look at the 12, character C is of L type, so we need to put position 12 at the C bucket, at front of the C bucket. C bucket is here, front is right in here of this bucket. So we put position 12 in the front of the C bucket in the suffix array. Next position is 1. 1 minus 1 is 0. 0 character is D of L type. L type is good, that's what we want. Put position 0 at the D bucket in front of the D bucket. This is D bucket, front is here, put it 0 here. Next one is this 4. 4 minus 3 is 4 minus 1 is 3. 3 is L type, it is R. Put position 3 in the R bucket at the beginning of the bucket. 3 goes right in here at the beginning of the bucket. 6 minus 1 is 5. 5 is L type. Put it in the C bucket. Position 5 goes in the C bucket in the front. The next front available in C bucket is here, 5. 8 minus 1 is 7, L type, D bucket, front. 7 goes into the next available front of the D bucket, right in here. 11 minus 1 is 10, position 10 is L type, bucket is R. 10 goes in the front of the R bucket. The next front of the R bucket is here, so 10 goes right in here. The next valid position is 12. 12 minus 1 is 11. 11 is S type, we ignore it. 5 minus 1 is 4. 4 is S type, we ignore it. Whenever you see 0, just ignore it. 7 minus 1 is 6, S type, ignore it. 3 minus 1 is 2, S type, ignore it. 10 minus 1 is 9, S type, ignore it. We finished left to right scanning of suffix array. Now we're gonna do right to left scanning, and if the position of the SA minus 1, if SA at current position I minus 1 is of S type, if S type, put that position in the back of the corresponding bucket. Let's see how we do it. We start from the end of suffix array. Take this value, subtract 1 from it. 10 minus 1 is 9. Is it S type? Yes. What bucket do you need to put position 9? Into the B bucket, at the back of the B bucket. 9 goes in the back of the B bucket, right in here. Next position is 3. 3 minus 1 is 2. 2 is S type. 2 goes into the B bucket. B bucket, at the back of the B bucket. The next back bucket available spot is here. 7 minus 1 is 6, S type, goes into A bucket, at the back of the A bucket. Position 6 goes at the end of the A bucket. At this point we're overwriting whatever it is in there, so this will be overwritten with 6. Then next position is 0, just ignore whenever you see 0. 5 minus 1 is 4. 4 is S type, goes into A bucket. This will be overwritten with 4. 12 minus 1 is 11. S type, goes into the A bucket. 11. End bucket. 9 minus 1 is 8. 8 is S type, goes into the A bucket. A position goes into the A bucket. In the back, next back available is here. 2 minus 1 is 1. 1 is S type, A bucket. Will be overwritten with 1. 6 minus 1 is 5. 5 is L, ignore. 4 minus 1 is 3. L, ignore. 11 minus 1 is 10 of L type, ignore, because right now we're only paying attention to S type. 8 minus 1 is 7. 8 is L-type, so we ignore it. 1 minus 1 is 0, L-type, we ignore it. 13 minus 1 is 12, L-type, we ignore it. We finished a right to left scanning of SA. At this point, our SA contains 13, 1, 8, 11, 4, 6, 2, 9, 12, 5, 0, 7, 3, 10. Now, whatever starting positions are of LMS substrings, and you see all LMS substrings start with A or $sign, all of them are right now, these two scans from left to right and from right to left, sort LMS substrings in alphabetical order. Notice that substring that starts with index 1 is this, arbor, and it is less in alphabetical order or equal to the string that starts at index 8, which is also arbor. Then position 8 is arbor, next position is 11, AC $sign. AB is definitely less alphabetically than AC. And if you look at this string, AC $sign, and the next string at 4 position, ACA, AC $sign is less than ACA because $sign is less than A. And let's compare 4 and 6. 4 is ACA and 6 is ADA. ADA is greater than ACA, so it is stored after LMS at position 4. So these two steps sort alphabetically LMS substrings, and that's what we need to collapse the original string S into a new string, which we're going to call T1, and this string will be shorter. In T1 string, each character corresponds to each separate LMS substring. Because LMS substring partition the original S, then if we substitute instead of arbor a character, just one integer character, and one integer character for this one, and one integer character for this one, then our T1 will be shorter than the original string S. And that's what we need. So how do we name LMS substrings? We're only going to name LMS substrings in the order they appear in the suffix array. You only right now paying attention to the starting positions of LMS substrings. Starting positions of LMS substrings is 13, 1, 8, 11, 4, and 6. Everything else is not starting positions, of LMS substrings. So we need to scan from left to right in this order, because in this order they already sorted alphabetically, and give consecutive integer names starting with 0 to all LMS substrings using this rule. If they are the same as in case arbor, then we give the same name. The name will be the same. If they are different, then name will be assigned the next available integer. And we start naming with 0. The first LMS substring is 13. It is just assigned name 0, and these array names will hold our names at the starting positions of the corresponding LMS substrings. Position is 13. This is position 13. We're going to assign this LMS substring name 0. The next LMS substring is at position 1. LMS substring arbor is different than LMS substring starting position 13. So we assign LMS substring arbor a different name, the next available. The next available name is 0 plus 1 is 1. So we put 1 at the position 1 here. Position 1, we put the name 1. So name 1 is assigned to the LMS substring arbor. Let me in fact put their names right in here next to them. I'm going to put their names right in here in green next to them. This is name 0, this is next name 1. Okay, and now the next LMS substring is 8. We only compare substring, LMS substring starting at 8 with the previous LMS substring starting at 1. 1 and 8 are the same, so LMS substring starting position 8 has to have the same name as LMS starting position 1, and the name is 1. And we put this name 1 into the starting position 8 in the array names. 1 goes here. Now the next LMS substring is at index 11, and the previous LMS substring just before 11 is 8. We need to compare them. 8 and 11, are they the same? No, they're not the same. So substring at position 11 will have the next name. Next name is 1 plus 1 is 2. So we put name 2 at position 11, and I will put 2 right in here. So we can visually see that LMS substring AC $ has name 2. Next, we compare the next LMS substring 4 with the previous 11. 4 ACA is not equal to AC $, so 4 will be assigned the next available name is 3. Take the previous name, add 1, will be 3. And we're gonna store this name 3 at position 4. Position 4, name 3 goes here. Next LMS substring is 6, compared with LMS substring at 4. 6 and 4 are different, so we need to assign LMS substring ADA the next available name, which is 3 plus 1 is 4, and that name goes into position 6 of array names. 4 goes here. We are done assigning names to all LMS substrings. If you visually look what kind of names we assign to LMS substrings right here, Abra was assigned 1, so the entire string Abra here will be replaced with character 1 in T1. The next substring is ACA. The entire ACA will be replaced with its name 3. An entire ADA will be replaced with name 4. Entire Abra will be replaced with string with the name 1, and finally AC $ will be replaced with name 2. So as you can see, we contracted the original string S into smaller string that consists only of 5, well, I didn't finish actually. This substring, the last substring that is only of 1 character $, is assigned name 0. Our any string will always end with 0. So the T1 will be 134120. How can you find it? Using your array, you scan the array names, assume that you initialize it with -1. If it is not -1, then it is a name of T1. So push back this value into T1. 1, 3, 4, 1, 2, and 0. This would be our shortened string that will be passed to the next recursive call in SAIS algorithm.